Well, good morning, good evening to hams, both locally and around the world and all the time zones by the magic of YouTube. This is Bill Ragsdale again with our lesson number 3 in our series on repeater operation and maintenance. For our presentation tonight, here's what you're going to receive. We're going to cover a selected list of must-have and should-have test equipment, familiarize you with what it looks like and what it does, how to use it, and then we will do some basic performance measurements that you would make. In addition, there's a fair amount of RF technology we'll get intermixed. And next week, we're going to go into advanced testing using a service monitor. I target the session to be 45 minutes long, give or take, and then we'll have an open question and answer session after that. The sessions are posted on YouTube. The first 2 lessons are already posted, and this will go up in a day or 2. The slides will be posted on our Slack site. I haven't finished prepping that site, so you'll get an announcement when the Slack site is ready. For access to that site, go to barkradio.org, which is our club website, and the training page, register on it, and you'll get on the list for Slack access. As a way of quick introduction, I'm Bill Ragsdale, K6KN. I'm the president of the Berryessa Amateur Radio Club, centered in Yolo County, Northern California. I was originally licensed at the age 15. It was a novice ticket, good for 1 year, non-renewable, and I went on to other discoveries, so the license has lapsed for exactly 50 years. 2005 I renewed, and the rest is ham history. The sessions so far, our first one was managing a ham repeater. The second one covered the components of the repeater and their functions. The session today is going to be on test equipment and making tests. And then we're going to go into advanced testing, the critical measures for a repeater, and then finally into repeater diagnostics. There'll be an optional hands-on training session either at my home in Woodland or at the BARC site at Berryessa Peak. And as a quick reminder, we asked you last time to download and review the data sheet for a watt meter. Anyone will do, just to get familiar with what the terms are. The Bird Model 43 is the old workhorse, the granddaddy of them all, or the new Model 4410 series. We can talk about this in the question and answer session. And also, the MFJ 246N is a very good alternative to that. Very nice piece of equipment. A few terms to get us started for today. The first is reflected power. Imagine you are the final stage of the power amplifier at your repeater. You're looking out through the filters and the cavity filters to the antenna. Because impedance mismatch, a certain amount of power will be reflected back to you as the transmitter, and we try to minimize that reflected power. One measure of that reflected power is called the standing wave ratio. It is a unitless number. It is just a number that is 1 or somewhat larger, and the larger the number, the worse the standing wave ratio. There are good numbers, and we'll talk about the range of the good numbers. Another key element is called SINAD. This is signal against noise and distortion. It is a very advanced, very clever method of evaluating receive sensitivity. We'll talk about that a little bit later. Watts, of course, is the measure of electrical power. It is volts times current. And so if you have 1 watt times 1 volt, that gives you a 1 watt of power. But that's as far as we're going to go into that. Decibels, named after Alexander Graham Bell, the decibel. He was the inventor of the telephone. Abbreviated dB, it's a logarithmic scale we'll talk about in some detail. And finally, service monitor. This is an integrated piece of test equipment. It includes a calibrated receiver, transmitter, CRT screen, oscilloscope, signal generator, digital voltmeter. It's all the test equipment you need in one box to maintain a repeater. And that's on our would like to have list. The must-haves. These are the simpler, more economical elements. The first one, of course, that we all have is a cell phone for photos, because when you're at the site itself, certain elements you want to take pictures of, equipment and so on. And also, if you have test equipment with a visual screen, you want to take pictures of some of those screen displays to put in your notebook. And also, you'll be calling an off-site testing partner. So when you're making changes at your repeater, you often want to check to somebody in the field to say, how are things working? Secondly, you need a handy talkie transceiver. Anyone will do, because this turns out to be a very flexible RF generator, which you can use for a lot of your test work. And you also need a digital voltmeter. Go cheap. Go to Harbor Freight. They're under $20. Don't spend a lot of money on a digital voltmeter. Some of your other test equipment will run $200 to $300, but there are bargains on the voltmeters. And you notice we have that Y-shaped cable on the right. Well, these are the Anderson power poles, because all of our connectors in our repeater for DC power are equipped with Anderson power poles. By having a Y connector, we're able to monitor a connection while it's in service. So having a Y cable is essential for voltage testing. Some of the must-haves, as we mentioned earlier, is a watt meter. Now again, I use the Bird just because that's the one I own and I'm familiar with, but there are numerous other watt meters on the market. And as you see here is the MFJ 267. This has a particular advantage, is in it there are dual meters. There's one for forward power and one for reverse power to give you SWR, but it also contains a dummy load. And so this could save you the expense of that additional item. And speaking of dummy loads, it's essential that you have two 50 ohm dummy loads. For power use, either a 500 or 100 watt dummy load. This is for testing on your transmit side. And then on the receive side, or for testing passive components, you need a small, easy to handle 1 to 5 watt dummy load. In this case, it's built right into an end connector. Another must-have piece of equipment is a graphic analyzer, and I stress the word graphic because we want the images to be done, or the testing to be done, over a range of frequencies, and the graphics analyzer scan and display the results. At the right we see the AA230. It is by Rig Expert. I've used one of these for a number of years. It is very convenient for handheld. It's the case is lined with a soft liner and a large keyboard, and there's enough labeling on the keyboard that you can tell what's going on. One of my favorites is the MFJ 226 antenna analyzer. Unfortunately, this is discontinued. You may be able to find it on eBay, probably at an advantageous price, maybe $25 to $50. MFJ no longer supports it, but and the labeling the keyboard is very, very limited, but it is lighter, smaller, and more durable. It's my preferred unit right now. And surprisingly, I do not recommend the most popular antenna analyzer on the market, the MFJ 259. The reason is it is non-graphic. It has meters on the front. It is very flexible, very powerful, but it is really intended for bench and design work, not for use in the field. It's very frustrating to do work with this because you have to keep extensive notes to try to remember what were the frequencies and what were the results at different frequencies. As I've said, the graphic view of the SWR allows you a quick evaluation of many of the components. You can check antennas, feed lines, and filters with the graphic view. Another nice to have item, not essential, not critical, but it's an AC line monitor. It measures your line voltage, your AC utility power coming in, the current consumption of all your equipment, and also VARs, which is for an inductive load. This is pretty far out, but for inductive loads, it's slightly different than the power value, and it'll measure line frequency. Some of the should-have equipment, which you probably would automatically have, are crimping tools. At the bottom left is the crimping for the Anderson connectors. and on the right is a crimping for the center connectors for the coaxial cable connectors. On the right is my tray of connector adapters. Going to Hamfest is an ideal time to pick up connectors because you'll usually find people with bucket loads of different adapters, and you pick out a selection that will fit all your conditions. We recommend, of course, you do not use adapters for permanent installation, but it's essential that you have them available as you interconnect test equipment. And finally, you need some uninstalled connectors for repair. This is a bonus item. I came across this at a very advantageous price on eBay, and it is a Decade RF attenuator. It has the outer dial adjust by 10 dB at a time from 0 to 90. The inner dial goes from 0 to 9, so I can dial an attenuation in from 99 dB down to 0. We'll talk about this for testing later on. And then you'll need coaxial jumper cables for troubleshooting. You should have a couple of 18-inch jumpers with RG400 or RG214. This is instrument grade double silver shielded cables. They're 98% shielding. They're rather stiff though, but these are essential for use with a service monitor. For less critical, non-essential testing, Pasternak RG8X is a good choice at 95% shielding. It is like the regular RG8, except it has an insulating layer between the braid and between the foil on the outside. Now we delve into some theory. As we all know, VHF is generally line of sight. That is, it is not reflected by the ionosphere, so antennas, transmit and receive antennas, pretty well have to be within line of sight. There can be a little bit of fringing, but line of sight is the rule. Earth and buildings, of course, attenuate, and trees and rain will attenuate a little bit. Now let's talk about some antenna theory. An isotropic antenna is a physics construct of an antenna that radiates in all directions. You see the diagram at the bottom right with a sphere with a little red dot in the center. Well, imagine that the radiation goes from that dot in the center equally to the entire interior of that sphere. That is an isotropic, totally non-directional antenna, and it is only theoretical. Real antennas radiate. They radiate less upward and downward, and they have some degree of directionality in the horizontal direction, and that is called the gain. So the unit of measure is the dBi. I stands for isotropic, and if you have a 3 dB gain, 3 dBi gain, it means that you have a horizontal direction has 3 dB more gain than it would have if the antenna was the theoretical type. Let's delve into dB itself. The dB stands for decibel or tenth of a bell, and it is the ratio or change between two power levels. Now there are three kinds of dB. The first one now is a change between power levels. If you cannot say I have 5 dB, because you have to say I have 5 dB above or below some starting point. So it's all relative. For example, if you have a 10 dB shift, that is 10 times the power. So if you had 1 watt with a 10 dB gain, you would now have 10 watts. You all probably know that 3 dB is 2 times the power. 3 dB gain means double the effective power. If you have a 3 dB loss, then you have 1/2 the power. To help you on these calculations, get the app dBCalc. It works on Windows, and I'm sure it must work on the other styles of personal devices. But the dBCalc gives you all of the power, dB, signal, and voltage calculations. Very useful. Now let's talk about the use of dB. The attenuation effect of individual radio devices can't be added. If you say I have a 10% change and a 10% change, it does not equal a 20% change. The results have to be multiplied. So a 30% loss coupled with a 30% loss is not a 60% loss. The math is shown there. You have to take the 0.7, which is the transmission without loss, multiply them together, subtract from 1, and it'll give you a 51% pass-through or a 49% loss. Well, that calculation is a nuisance, and dB simplifies this because decibels can be added and subtracted. Their structure is the equivalent of multiplying. They're logarithmic. So in this case, a 30% loss is minus 1.55 dB, coupled with another minus 1.55 dB loss, totals a dB loss of 3.10. We can add them together. If you look up on one of the tables, you'll find out that is a 49% loss. So we get our power change based on simple addition and subtraction. The next flavor of dB is dBm. Well, now dBm is an actual electrical power value because it has a starting known value. And that starting known value is 0. So 0 dBm is set to be 1 milliwatt, 1,000th of a watt. That's home base. An HT, for example, that has 5 watt output is 37 dBm. That is, it's 37 dB above 0. If that HT loses 1/2 of its power, which is 3 dB, then the power change is its original 37 minus 3, or 34 dBm. Look that up, and you'll find out that is 2.5 watts. And we've discussed the isotropic antenna. The 3 dB antenna means that you get twice the power irradiated directionally. And remember now that it doesn't create that power. It does not really amplify it. It means it redirects it. Instead of the power being vertical, up and down, it goes more horizontally. Now let's talk about transmission loss. The transmission loss is the major factor contributing to effectiveness of communication. The further away you are from a transmitter, the greater the transmission loss. There's a chart on the right, and this chart is from years and years and years ago, because if you look carefully, you can see the scale factor is an MC. Well, that's megacycles. So back before we began to use hertz for a cycle per second, we used cycles. The lowest line is 144 to 150 megahertz, megacycles, and that's identified by, highlighted by the red line. So at the bottom left, at 0 distance, we have approximately 120 dB. This means if you get a few hundred feet, a few thousand feet, a mile away from an antenna, you would probably see a path loss of 120 dB. At 75 miles, it is a range of 190 dB. So repeaters and HTs and all of our radios have to cope with a fantastically large range of signal from this minus 120 dB loss down to 190. Our goal as repeater operators is to maximize the radiated power and then minimize the received losses or improve our sensitivity of our receiving. And we have to live with the path loss because that's physics, that's the environment. So here are some examples. This is the transmission loss to a user. Imagine our transmitter is 60 watts, that's 48 dBm. And then we have somewhere between 1/2 and 2 dB of loss in the cavity filters, and something in that same range for transmission line loss, a dB or 2. The benefit is that we have between 3 and 9 dB antenna gain. A short vertical quarter wave antenna would probably have a 3 dB gain, and a elaborate professional grade antenna such as you use on a repeater might have 9 dB gain. The path loss, again, as we said, is say minus 120 to minus 190. So this, subtracting them out from our starting point, gives us a number somewhere in the range of 80, 90 dB, minus 80, minus 90 dB of the power that is available at the user's end. Then there's, say, a 5 dB loss in the user's antenna. And so into the transceiver, you get about 91 dB. And this, of course, has a very wide range, but this would be typical. Now, a typical receive sensitivity is minus 120 dB. So we have that slack between the 90 and minus 120. Here's the entire scale graphically. Minus 48 dB is our 60-watt repeater. The HT is at 37 dBm. A Christmas tree light bulb is about 1 watt, and that's at 30 dBm. And then 1 milliwatt, which is our reference point, is 1,000th of a watt. About the highest signal we can expect in the field is about minus 70 dBm. This is after our path loss, which, look at that, that is 1/10,000th of a microwatt. Pardon me, 1/10,000th of a milliwatt. And the optimum lowest level would be about 90 dBm. This is 10 to the minus 12th. That is 12 zeros followed by a 1, which is measured in the femtowatt, the picowatt and femtowatt area. And the receive limit is about minus 120 dB in most receivers. This is limited by semiconductor technology. And that was the equivalent of 15 zeros with a 1 for a power level. So now let us visit the repeater site. We're driving up to Bark Repeater. It's a 20-mile drive on a dirt road going up 3,000 feet. And we have a 2-person rule, which means we don't go up alone. If someone has an accident up there to repeater site and we need help, it could be a simple, something simple, broken leg or whatever. It could be worse, but we need someone to sense, drive, and take care of one another. Having a log book is essential. Again, you log everything, because if you come back 2 or 3 months later, you need help in remembering what were your observations. And then inside our toolbox, we want to have a key to the vault, AAA batteries, flashlight, water, paper towels. And the paper towels do double duty as toilet paper. I remember one time we got to the lower gate of our repeater, and I turned to my partner and I said, "Oh my gosh, I forgot the key to the vault." So we had to turn around, and that was the end of the day. And some of the pros carry a chainsaw. We don't, but usually the site we're at does have some question about downed trees. However, we're usually never there after weather, so other people have taken care of road clearance. So once we're at the repeater site, let's look at what do we do on arrival. The first thing we do is we make a RF power check on arrival. Add your power meter in, test the transmitter output power, because you want to be able to answer the question, what was it like when we arrived? And you also want to know that it is in proper shape when you leave. And that way, and again, your final step on leaving is do a repeater power test. So this way, beginning and end, you know everything was in ship shape. Then after you lock the door, and as you're about ready to leave, make one last RF check, because it's a long hike to come back and start over again. The next step we generally would do would be to check utility power. This is a matter of good housekeeping. In this case, we want to measure our utility DC power, our battery, and our solar power, to measure them open circuit. So the table down below on the left is under isolated. It says this is connecting our DVM to those items with no load all by themselves. Utility power, DC, we measured 13.7 volts. The battery was 13.5, and the solar was 22.6, and that's a typical for solar. That's expected as the open circuit voltage. Then we connect each individual item to the repeater and unkeyed. So now we're looking at the idle draw from the repeater, typically 3 or 4 or 5 watts. So the utility power in this case, driving a repeater was 13.5 volts. The battery was 13.41, and the solar was also 13.41. Then with each of these situations, you then key the repeater to make sure that the repeater can operate properly on that one power source alone. So in this case, you see our repeat values, and they're all in the 13.0 to 13.3 value. Again, logged for future use. Now let's start to look at RF performance. You should do most of your RF testing with the transmit RF forced off or into a dummy load. Otherwise, the users in the field are going to hear your tests, your chunks, your tones, and your whistles coming over the repeater. Now, if you do have to make a test with the antenna on, then make a voice announcement at the beginning and the end. Otherwise, the users may think something malicious is going on, or they may end up calling a control operator to say your repeater's having trouble. Here are some of the power measurement. Notice there's an error on this slide. At the right, it should not be a dummy load. This should be your actual antenna. So in this case, at the bottom, we have the repeater output going through a power meter, going to the cavities and our antenna. So in this case, our meter is telling us the reflected voltage, the reflected power. So we're putting out, let's say, 60 watts to the antenna system, and due to impedance mismatch, what is the reflected power coming back? If it's in the range of 2%, 3% for a 60-watt transmitter, this would be in the range of 2 or 3 watts coming back reflected. That will work out to be an SWR of around 1.4. 1.1 to 1.4 is as good as you can hope for. That is very, very good. A little bit higher range, possibly due to cavity tuning, maybe longer feed lines. Sometimes connector mismatch will cause a little reflection on impedance. So an SWR in 1.5 is fine. When you get up around 1.7, little alarm bells start to go off, and anything above that really needs attention. So let's see how we can make the graphical view of SWR. The test before we saw was reflected power. The SWR is calculated from reflected power, but the equipment does that for us. So it will allow us to do a visual wide frequency sweep of our antenna, feed lines, and filters. Ideal for troubleshooting. It's handheld. You can even do it hanging from a tower. So the two that I prefer, the one is the Rig Expert, as I mentioned earlier, the 230 or the MFJ 226. There are many others on the market. It's kind of a competitive field these days because microprocessor technology makes this a very effective product. And as I said, not the MFJ 259, no graphic output. This is what the output display works on a single cavity filter. It's pretty broad here. It's wide because this is the taken off of my 226 with my cell phone. And for some reason, the SWR is 3.67. I'm not sure why, but this was taken just for our test purposes. So the SWR is showing us the reflected energy back at the range of frequencies, and the SWR increases to the left and to the right. Good for a quick check. You'll see later that the alternative method is what's called a return loss bridge into a service monitor. It gives us similar information, but it's a little more precise. This allows us to check cavities, feed lines, and antennas. Or you can check the antennas alone. If you're checking all 3 devices, cavities, feed lines, antenna, you need no extra termination. But if you're testing cavities alone, you need to terminate with a 50 ohm resistor at the far end. So this is what the test would look like. You have your 226 with the filters, and then either the small 2-watt dummy load or off to your antenna. Test them first as a whole sequence with them all there. If you get an SWR under about 1.6 or 1.7, case closed. If you have a deviation from that, you may have to go into troubleshooting because there may be a case of damaged feed line, damaged antenna. In that case, you can test one item at a time. To interpret them, you look at this chart, We saw it earlier, a little bit earlier, and this does the reflected power conversion back to SWR. 1.4 is great, 1.7 is worse, 1.7 and higher, watch out, take care of it. Also, the analyzers can locate cables open and short, and they will give you a distance reading to that defect. We were doing troubleshooting at one of the hospitals here, and they had a feed line problem. And from inside the building, we were able to find out how far along that feed line the problem was. And we walked to that particular area and found a bad connector. Squelch. Squelch is the muting, of course, of a receiver in the absence of any input signal. And there are several ways to set squelch with increased level of precision. The first is swag, which is scientific wild-ass guess. In this case, you turn off your tone, your CT/CSS tone, and you decrease the squelch until noise appears. This is typically what you do on your home base station. You turn until the squelch disappears, and then you increase a little bit to get silence, and then restore the CT/CSS, and you hope you're okay. And that is the bare minimum that you can do. You really don't know how high above your basic noise level you set it, but with no test equipment, that's the method. The next approach is to set the squelch from a calibrated RF source. In this case, you turn off the CT/CSS, and we will see a diagram on the next slide. You choose a handheld transceiver, set it to low power. You pass that through a calibrated attenuator. We saw a picture of that a moment ago, that little cylinder with the knobs on the front. Then you go through an RF sampler, which lets you connect this to your repeater without upsetting any of the impedances. And you locate that sampler between the cavities and repeaters. And again, we'll see a photo in just a moment. You increase the RF signal until the noise begins to decrease. That means you are just starting to hear quieting from that RF signal. Note that signal level, add 5 dB, increase your signal level to that point, and then set your squelch there. Now I put a question mark on this because the 5 dB is just a general rule of thumb, and it depends on variations in your noise level and who knows what all else, thermal variations to your antennas. So somewhere between 3 to 5 dB gives you a safety margin for a good squelch level. And finally, at the very end, make sure you restore the CT/CSS. So this is somewhat better than the seat of the pants version. This is what the diagram looks like. We see at the top left as our antenna goes through our cavities. This goes through the sampler into the receiver. The samplers normally have a 30 dB attenuation. So this isolates your test equipment from the main RF by 30 dB. This means you can inject and withdraw power, and it's 1/1000th of the power that's flowing through. In the bottom then you see, here we have, in this case, that diagram also is an error. That's not an HT down there, that's the antenna analyzer. Pretend that that's an HT plugged into the calibrated attenuator. Now this allows you to set the power level to just the bare minimum detected, and then add 5 dB, or we subtract 5 dB attenuation. Signal level goes up 5 dB, and then set that to your new squelch level. And then the proper way is to use a service monitor. We'll do that next week. To discuss the SYNAD, though, so you know what it's about, it is a measure of the signal above noise and distortion. So imagine the signal is your voice, and underneath that is noise and distortion, and SYNAD does a comparison between the two. To take the place of your voice, they always use a 1 kilohertz tone. So coming out of the RF modulated source is a 1 kilohertz tone. This goes into your repeater, and then from the audio out, the audio output is taken and analyzed. And the typical value in this is 12 dB SYNAD for a squelch setting. So after you can set your you adjust the RF value up and down until you get the 12 dB SYNAD. During this time, you will hear scratchy noise, you'll hear good tone, and somewhere in the middle is this 12 dB SYNAD, which has been, from the design standpoint, is the optimal point to set squelch. More about that next week. You set that to squelch at that point, and of course then restore the CT/CSS. Well, that wraps us up for today. We've seen the test equipment. We've seen some of the basic tests to do from power, from an RF standpoint. These are the things that you do with minimum test equipment to make sure everything is operating properly. Next week, we are going to get into service monitors. We'll discuss the product generations of the service monitors from about 1985 to the current. We'll discuss buying them new and used, the measurements that you can make with them, and the things you should be testing are things like transmitter frequency, the deviation, the IF centering, setting the squelch, and the descends. The descends is a critical value for repeater operation. And cavity filter tuning. They are graphic, so they allow you to a very convenient graphical adjustment of cavities. Of course, we know that cavity settings are extremely unlikely if they would ever have to be changed. So your assignment for next time, go online and find one or more service monitors and look at their features and their cost. You'll find their feature set is very, very wide. Transmitting, receiving, audio tone, signal analysis, distortion. They all have SYNAD. They have a feature called a tracking generator. So learn the features, learn the buzzwords. The typical brands that you find is one of the granddaddies of all is IFR. They were more recently purchased by Marconi a couple of years ago. Their used equipment on the market is under the IFR name. And another one, of course, is HP, has been in this for years. They spun off this equipment, and it is owned now by Agilent. And then Rigol, I believe it's an Italian firm, and they are making some very streamlined amateur, I think within amateur price range signal monitors. Also look for new and used. There's a thriving market on eBay. I've bought several service monitors, all of them bought off of eBay. References for the presentation today. The first, of course, is to go to barkradio.org for registering for SLAC. Then at the SLAC site, you'll see PDFs of these presentations. It's a chance for questions, answers, and the YouTube links. The YouTube channel is K6KN Bill. 2 sessions are posted there already. And the granddaddy of all of this is at repeaterbuilder.com, repeater-builder.com, and a goldmine archive of instruction books and techniques of repeaters. Very good. Secondly is the ARRL Handbook for Radio Communications and the ARRL Antenna Book. All radio amateurs should have those. They are in the range of 1,000 pages each, and if you have a question on ham radio, it ought to be in that book. And now we will stop the share, and we'll open up for questions as soon as I turn off the recorder.